I'm basically going to deliver Bill Green's talk about pressure effects on kinetics, so that you don't just spend all day watching videos. But if you are watching this on a video, like after the fact, just go and watch Bill's talk from 2023, because I'm not going to add much except mistakes. So I've added a little bit, but mostly he explains it very well, and I shall do my best. Okay. Okay, so starting off with the quote obvious pressure effects on equilibrium constants first. You learn in high school Le Chatelier's principle that if a reaction in the gas phase is increasing the number of moles of gas, then if you squash it, it will try to react in the other direction to counteract the effect. And so if you increase the pressure, it's going to want to compensate by like moving the equilibrium position. So you can change the position of the reaction by squashing it, changing the pressure. And yet we learn that equilibrium constants are constant, right? They're a function of temperature only. And so that suggests that the equilibrium constant shouldn't change as a function of pressure. And so sometimes people get a little bit caught up, and in undergraduate chemical engineering, you figure out how to resolve it. And so we'll spend a little time on that. So the dimensionless equilibrium constant doesn't depend on pressure. It's because it comes from the delta G. It's evaluated at standard pressures and therefore not affected by the actual system pressure, just a function of temperature. However, for ideal gases, your equilibrium constant is the sum of the partial pressures divided by the reference standard pressure to the stoichiometries, which means that if your stoichiometry changes, you've got more reactants than products or more products than reactants, you end up with this total pressure over reference pressure term left over to the power of delta nu. So your mole fractions, your yi of the mole fractions, will change if you change the pressure. So the equilibrium mole fractions, y, are affected by changes in pressure. Now, this is true if the number of moles of gas is changing due to a reaction, but also if you're adding an inert gas, because it dilutes everything. So if you've got some stuff in a tank and you add a bunch of argon, it's going to change the mole fractions just because you've got moles of argon in there in the denominator. Or if you don't add any argon but you squash it with a piston, you change the pressure, what happens in that case is there'll be a chemical reaction occurs, the equilibrium will shift one way or the other, and your mole fractions will change. So the mole fractions are affected by changes in P. For an ideal gas, the dimensioned equilibrium constant, which is Kc, so it's an equilibrium constant Kc of T, but now for concentrations, this is the concentrations to the stoichiometry, is going to be, for an ideal gas, you've got your partial pressures over RT, and so you end up with this P0 over RT term if you relate it to this one. And you'll see that this is also unaffected by pressure. So this is a function of temperature is now in there twice with a weird T to the delta, 1 over T to the delta mu dependence. But there's still no pressure. So your Kcs are not affected by pressure. Because Kc doesn't change, it means that your equilibrium concentrations won't change if you change the pressure by adding argon into a tank. So you've got stuff sitting in a tank, it's equilibrated. You put more and more argon in there, the total pressure goes up, but the concentrations don't change. They ignore the argon. So the mole fractions changed, but the concentrations didn't. If, however, instead of putting argon in, you squash the tank in a piston, you then cause the concentrations to change because you'll drive a chemical reaction. So all of these things do work out if you're careful enough about, are you talking about K equilibrium, Kc, did you get your reference states right, your standard states? Just be careful and it all works. And Le Chatelier's principle, your intuition you build up from high school does work with your undergrad thermodynamics. And so this is the obvious, quotes, pressure effects. They're obvious, but people still get it wrong.
Does the equilibrium constant depend on how you define the reference states?
The numerical value of it would. Yeah. And so, yeah, it's solvent people start getting, it gets more complicated. Like, is your reference state infinite dilution or 1 mole or whatever? So it gets harder, but ideal gases is hard enough. Okay. The kinetics. So the quotes, obvious effects on kinetics. So if your mole fractions are held constant, and then you isothermally compress to a higher pressure in a piston, your concentrations increase. So you've got a certain ratio of stuff. If you increase the total pressure, your concentrations are going to go up. Now, if your rate constant K, so the lowercase k's are always rate constants, or rate coefficients rather, if that's independent of pressure, then a unimolecular reaction is just one reactant, first order reaction. The rate per unit volume, R, is going to go up. However, because the definition of R is rate per unit volume, your volume went down when you squashed it. So although the rate goes up, the volume goes down, so the total effective rate, as opposed to the per unit rate, is unaffected. So for a first order unimolecular reaction, you squash it, it won't change the rate of per moles per second, won't change. If, however, it's bimolecular, for example, it depends on the concentration of one reactant and the concentration of the other reactant. It's therefore second order in total pressure. So the rate per unit volume is second order. The total rate in the full volume will go up to the first order because the volume went down. So that's if you're changing the pressure by squashing the thing. If you're changing the pressure by adding argon into your tank, you haven't changed the concentrations, right? The concentrations of your things hasn't changed when you put argon in there. And the rate constants are just a function of temperature. You haven't changed the equilibrium constants, either of them. And so it shouldn't affect the rate constants at all. So adding argon to a system to change the pressure should not change the rate coefficients or the rates or anything, according to the obvious pressure effects. But it does. And so that's what the rest of this talk is about, is like, why and how do things actually depend on pressure when all of the things we learn about rate constants and Ks and so on says they shouldn't. Okay, so it's because these rate coefficients, these lowercase k's, actually depend on more than just the reactants and the products and the temperature. So Bill's always very careful not to call it a rate constant. I've already slipped up twice today. But they're called rate coefficients. And so the solvent obviously also affects the thermodynamics, but there's kinetic solvent effects. If you've got an interface, you've got catalysis in there or something, that's going to affect the rates. If you've got photons or electric fields or all sorts of other effects, can completely change the rates. It's not just a function of temperature. Those effects are completely missing in RMG for now, but he's just kind of pointing out that rate coefficients depend on more than just temperature. And they depend on the pressure of the gas and the gas composition. So this can have a large effect. We'll see various, the biggest one that we worry about mostly in this talk is that at low pressure, you can make it slower to thermalize the reaction, slower to thermalize the energy levels than the chemical reaction, so you don't get a Boltzmann distribution. We'll explain this more in a moment. So that's the biggest effect. There are also smaller effects that at really fast reactions could be diffusion limited, and at really high pressures, you can end up with non-ideal gas effects. If the volume of your transition state is slightly different than the volume taken up by your reactants, then at really high pressures, there can be an effect due to that. But the main one we'll worry about is this thermalization type effects. So unimolecular reactions, the rate coefficients, I did it again. Rate coefficients are often pressure dependent in the gas phase. This figured out by Lindemann about 100 years ago. And we'll talk more about why. So this is unimolecular reactions of A goes to something. A goes to B or A goes to some other. Now, if you've got a very exothermic reaction that kind of forms a bond, this can have very large pressure effects. Fundamental issue here is that you need lots of collisions between the molecules to add or remove energy in order to basically define temperature, to make sure that everything kind of has the same amount of energy as it should for a given temperature. So I got some pictures in a minute to explain. But this kind of thermalization or getting everything to have the right amount of energy by kind of sharing energy by bumping into things needs collisions. It needs to bump into things in order to share that energy. So the time it takes to either heat up or cool down might be longer than the time it takes for the chemical reaction. And so that means that you never quite reestablish your Boltzmann distribution of energies, and so you then really don't have a definition of temperature, and everything goes haywire. So that's what we're worrying about. So this is, I added some pictures. They might be entirely wrong, but this kind of helps my perception of it. So this is an energy Boltzmann distribution of energies, a cold one and a hot one. It's not a Maxwell-Boltzmann distribution of kinetic energies, because that would go to zero at zero. But probability distribution. So the hotter you are, you're more likely to have more energy. And so the shape of this curve is basically the definition of temperature. Now I'm going to just flip the x and y axes so that now energy is vertical and my probability is out here. So we can see the cold one, you're more likely to have lower energies. So we could say, okay, this is my activation energy, and this is where Arrhenius expressions come from, that we'd say at low temperatures, there's a tiny little segment here of this blue bit is above the activation energy, has enough energy to react. And at higher temperatures, you've got a higher probability of things, a bigger population of stuff that has enough energy to react. And so the rate goes up. And so the whole Arrhenius expression depends on this. Now, why do things follow this Boltzmann distribution? It's because they're all bumping into each other randomly, and the probabilities of kind of sharing energy to a collision, there's kind of all the random statistics and stuff. You're more likely to share energy, averaging things out. You're unlikely to put all the energy into one particle in a box and have all the other ones have no energy and so on. So you end up with all these collisions and random collisions ending up with the Boltzmann distribution. But if you don't have enough time for those collisions, and you say, okay, all of these things above the activation energy react and disappear, but I don't have enough time for the cold ones to refill those energy levels, you could end up with a weird thing. You've depleted these states. And so suddenly it's not a Boltzmann distribution, and you can't even call it hot or cold because there's no such thing as temperature anymore, and everything goes out the window. So this is what we're trying to solve. So at high pressures, suppose we've got a reaction A and B reacting, and they form a molecule C. They form a bond. So two radicals come together. This chemical bond might have 100 kilocalories in. So there's a lot of energy released, and we go down to make this C. At high pressures, A and B come together. They make this excited C. It collides with M, which represents any bath gas, all of the collision, all of the other molecules in the gas. And they cool it down and make C. And so we have a reaction, A plus B goes to C. We might also then say, okay, C can react to make D, and then D can react to make E and F. And so we would put these three elementary reactions, RMG would discover them in our mechanism. And we've got three independent rate coefficients, K, and they each have Arrhenius expressions, and we can solve it. This is fine. We just think it's a sequential process of A and B makes C, C thermalizes and has an energy distribution, C makes D, which thermalizes, has its own temperature, and E and F come out. At lower pressure, you make the A and B combine, they make this C star, the excited C. But before they collide with enough M molecules to cool them down to C, they might skip across and make D star. But they might react further before they've had a chance to cool down. And then once D star, they might gradually cool down to make D, but that might skip across to make E and F. So now you have A and B react, you might suddenly make E and F without ever noticing C or D. In fact, this is how these things came about, that people measured and reported, oh, I found a rate of A plus B goes to E and F. And they said, here's my rate coefficient. They got a rate law and everything. And then people were like, wait, that doesn't look like an elementary step. I don't understand which bond broke. How on earth did you find a transition state? I can't find a transition state between A, B, and EF. And people realized, oh, wait, it's because it went through C and D. But it looks like one step. I mean, chemically, it is kind of, it's one step. But that means you've now got 6 rate coefficients because you've got A and B makes C, C makes D, and D makes E and F as before. But now also A and B makes D, C makes E and F, and A and B makes E and F. So all of these things are direct reactions, and you have your own rates. So the concentration, the rate expression for this depends on the concentration for these. But they're no longer Arrhenius expressions. Okay, so how do we solve this if we can't just use Arrhenius? We can calculate the time dependence from the population balance on every energy state of each of these things. So we've got our A and B, our C is a middle. We're not worrying about C and 2 wells. We're going to do a case with just 1 well and then the products. If we say that each one of these energy levels is kind of a separate, quote, species, a separate thing that we're tracking, we can now say I've got a transition from A and B at a certain energy to making C star at that energy. And so I've got a K, my K is now a function of energy, not of temperature. And so these are the collision, the Ks of E, the rate coefficients as a function of energy. We then worry about the collisions that can change the energy between the energy levels. So this is going from C star down to various different energy levels. So these are the collisional energy transfers, these omega. We also care about the densities of states. So if we've got lots of possible energy levels here, then the rates will be faster. And so it depends on how many possible energy levels there are. But we kind of worry about the density of them rather than the number of them. Yes. Yeah. The question is, are these vibrational energy levels? Yeah. So it's a combination of all the energy levels. We will mostly calculate them from vibrations or hindered rotors and so on, but all the energy ways that these molecules can hold onto energy. I think most of the electronic ones are separated far enough above that that we're in one.
Rotational status.
Yes, so rotational stuff, yeah.
I guess translational.
So we can calculate each of these little rates and energies, and we can also estimate them all. So RMG does a lot of estimating. Arcane can take, if you've calculated them all, you can feed them all into Arcane and it will calculate. So if you've calculated the molecules with quantum chemistry, you can then find, as you said, all the vibrational frequencies, hindered rotors, feed all that into Arcane. It will calculate all of these densities of states and rates and stuff, and we'll solve this master equation. And then also that if you're in the context of RMG, it will estimate an awful lot of these parameters. Okay, so the densities of states is how many distinct quantum states a molecule has in a certain energy range. And so that's this, the E, the density of states E. If you integrate this, you can get the microcanonical, the Q of temperature, which is related to your thermochemistry. But this is a Laplace transform. And then your microcanonical rate, these are the K of E. If we do this Laplace transform, we get the infinite pressure, the high pressure rate constant, rate coefficient. Okay. So this is a way to get your overall thermodynamics of a molecule and your overall high pressure limit rate coefficient from the microcanonical ones. And so RMG can do the inverse Laplace transform to guess or figure out these K of E and the rho of E from the thermodynamics and the high pressure rate coefficients, because that's all we have in RMG typically. So RMG looks up in its rate estimate thing database, K infinity, the high pressure rate coefficient, and your thermochemistry. And so then we, through a combination of functional group definitions buried in there somewhere, to say kind of, oh, look, I've got a methyl group that's going to add these vibrational modes and hindered rotors, and I've got some other kind of groups. It will estimate many of the vibrational frequencies, and then it will figure out the rest using inverse Laplace transforms to estimate stuff. All right, so the next challenge is that this master equation, once you solve it, which is not trivial in itself, then just gives you thousands and thousands of energy states evolving over time. So it will say, okay, your amount of really excited A is changing over time. Your amount of all of those these little states are evolving over time, but that's not the rate coefficients that you want. Yeah.
Solving the state. Calculate some sort of eigenvalues and stuff, but they're probably the stationary.
The question is, are you solving the steady state of this master equation? No, I think you're getting the time dependent, but then how you extract the rate coefficients you want, and there's several different methods to do that. Some are good, some are bad, but mostly it depends on the context. So getting the overall phenomenological rate numbers that you want out of this master equation solution is non-trivial. But so the different ways have been proposed. There's the modified strong collision, which is probably the worst, and therefore the one we recommend. Because it's robust. And all the other ones work well except when they fail, and then they fail horribly. And so in RMG, where you want the whole thing to be fully automatic and just work for everything and work for really bad estimates, because RMG is going to throw really bad estimates at it. You want something that's fundamentally robust. And if it's off by a factor of 3, well, probably everything else is off by a factor of 3 as well. If it's off by 2 orders of magnitude, it's probably not your biggest error. And so the modified strong collision is what we normally use while running fully automated RMG. If you're taking the time to run Arcane on a master equation where you have calculated all of your vibrational frequencies, your hindered rotors, you've got your energies right, you've calculated your transition states, don't use modified strong collision. Use the chemically significant eigenvalue, the CSE, is usually better. There's some backup slides at the end, might not talk through, but they're in the PDF that kind of describe a little more the difference between them. They're also described nicely in this series of papers. So even the best one, the chemically significant eigenvalues, has challenges. This is where you kind of separate out the fast modes and the slow ones, and you say these ones probably represent chemistry, and those ones don't represent, they just represent energy transfers, and so you can extract the rates. Okay, so at low pressure, these well skipping, oh, that was all, yeah. This is all about errors in the parameters. So the fact that we've estimated a lot of the input parameters, and then we've solved it approximately, and then we've extracted stuff with approximate methods. Those are all going to end up with uncertainties or errors in the parameters. But as we heard yesterday about RMG, there's also the model truncation error, not just the parameter error. And the same thing is true here, that you might be missing pathways. So the idea is that this well skipping that we talked about makes A plus B makes E plus F, means that there are reactions in our model that don't correspond to a reaction family. There is no reaction that makes A, you can break the bonds in A and B and make E and F. So RMG has to kind of expand this network, and it's very similar to the core edge model that we worked out for a whole reaction model, except just for a pressure-dependent network. Okay, so usually there are lots of intermediate keep on moving stuff around my screen. Lots of intermediate wells, lots of isomers of C, and lots of multiple product channels. The pictures we've seen so far only had at most 2 wells and 1 entrance, 1 exit, but there's usually lots. I'll show you some in many slides' time. And so which ones do you want to include in the kinetic model? So it's similar to the species selection stuff we heard about, and we'll hear more about in half an hour, but with some little twists. There's good documentation in this pressure dependence theory guide. So if you go to the RMG website, follow the documentation, go to the theory guide, not the user guide. So it's not how to run RMG, but the theory behind it. In there's a pretty good guide that talks through this. So I recommend that. But the rough approximation how it works. You react A with B, and it discovers it makes C. But then it says, and this is above the tolerance, and so it says it wants to put C in the model. But if you've turned pressure dependence on in your input file, it would say, A and B are forming a single unimolecular thing. This is going to be pressure dependent. So instead of just putting C in the core, it will put it in a PDEP network. And then it says, okay, I've now got to explore this PDEP network. So it will then explore the reactions that C can do, or more accurately, C star, by applying all of the reaction templates. And it will say, okay, I can make D. Now I need to decide whether D is important or not, based not just on the concentration of C in a simulation, but based on this C star. So we need some edge flux to decide if the rate that we could make D is above the characteristic flux to make it into the core. But we don't yet have a full pressure dependent network. So we can't solve this because we don't have the full network. So we can't decide whether we need to include D because we can't find the rate of D. And so we can't decide whether to expand it. So what we do is we try to overestimate the rate at D could be made. And based on that, we can decide, is it worth exploring, or is it definitely not important yet? So based on the overestimate, we could say, okay, this is big enough that I need to worry about it and I need to explore it further. And it's possible to get an overestimate from an incomplete network. So that's the crucial part, that you can't solve what you need until it's already there, but you can solve an overestimate with a partial network. And that allows you to decide whether to keep exploring the network. So using that overestimate, it decides that D is important. And so it adds D, but it knows that D would also be chemically activated. So instead it adds D star to a new PDEP network, so that you'll end up with another pressure dependent network that's slightly bigger. And then it explores that, and similarly. So then it would find E and F. And then it could say, okay, I've now got solve the master equation for this whole thing and find a rate coefficient not only for A and B makes C, A and B makes D, A and B makes E and F. And then it would put all of those on the edge of your RMG model. And then RMG would decide, okay, E and F are important, and end up in the core eventually. This overestimate of the pressure dependent rate coefficient is based on our high pressure limit. And so these are all based on the estimates from the RMG families. We keep track of all of these partial PDEP networks based on their entrance channel. So we'll end up, if you look, I mentioned this later, RMG, when running with PDEP mode on, will create a little folder called PDEP with hundreds of files in that has these PDEP network descriptions. They're all numbered sequentially, and they're all tracked by basically what's the entrance channel, A plus B. And then there's several versions of each as it gradually expands them. So it saves a copy every time it expands the network. The algorithm is very similar to how RMG builds up the core model. And only after adding all these reactions, we get rid of the activated D star. So in your final RMG model, you don't see these excited D stars. You just see the overall effect of does it make the wells, the bottoms of the wells. So here is what I mentioned, that when you're debugging weird pressure dependent stuff in RMG, or rates that show up in your final model and you can't figure out what family they came from, or something's gone weird, it's often pressure dependence. There's a folder comes in your output called PDEP, and in it there's all of these network files. These are all Arcane input files. So you could just take one of those, run it in Arcane, and it will solve everything, draw you the little picture of the PDF. And that's a good way to start figuring out what's going on in your network, which elementary reactions or which energies could be causing the issue. A warning that although I just said this is a really helpful way to debug your mechanism, they're in fact utterly misleading because they're all wrong. The mechanism, the arcane jobs that RMG does while running, I'm convinced are correct, but these arcane files are currently wrong and misleading. We should fix this fairly soon, but just a caveat, it's not yet fixed. Keep an eye on this pull request to see when we actually fix it. It's just there's an energy offset. All the transition states are offset by a constant energy. We need to fix it. It's a probably fairly easy fix, but just a caveat. It's still a very helpful thing to look at, but yeah, beware that for now it's slightly wrong. Okay. So after you've done all of this, you've run your your master equation, but you then want to get rate coefficients to put back into some mass action thing like Cantera or RMS or Chemkin or something. You need, therefore, something that describes A plus B goes to E and F in some parametric form. So the three different types, there's the high pressure limit, which we're all mostly used to. This is what, if we hadn't even turned on PDEP, would just be the rate constant, rate coefficient, times the concentration of A and B. And we'll call this K infinity to remind us that it's assuming the high pressure limit. I'm going to skip down to the low pressure limit. Here, it's A plus B plus M, where M represents everything. So all other molecules in the system acting equally, because all they have to do is collide. They don't have to react, so it doesn't matter what they are, is the idea. And so suddenly it becomes third order instead of second order, or second order instead of first order. There can be extra efficiencies because sometimes certain molecules are more efficient at transferring energy when they have a collision, and some are less efficient. And so you can add extra coefficients in here to say, count this one double or count this one half. Anyway, in between those, there's this pressure-dependent rate coefficient where we put the plus m in parentheses to say that it kind of matters, sometimes matters. And this is going to fit a smooth curve, I guess, between the high pressure limit at high pressures and the low pressure limit at low pressures. And in between, you're kind of 2.5 order or something weird. So clearly there's no nice parameterized form for 2.5-ish order. And so people have come up with different ways to try and fit it. So for fall-off ones, TROA works fairly well. And it basically says you've got a high pressure limit that's Arrhenius, a low pressure limit that's third order Arrhenius, and then a couple of more parameters to say how does it smoothly join the two. Chebyshev is a way to parameterize it as it's a kind of second order, a polynomial in 2 dimensions of temperature and pressure with a bunch of coefficients. It's hard to interpret. It's just like a matrix of coefficients for a polynomial. So you can't look at it and it means anything. But it can describe, it's pretty universal. You can describe any shape and you can describe weird dependencies and stuff. So Bill likes that one. A lot of people in the community have published a lot of models in log-p format. If you watch Bill's video of this, he has some hilarious sighs and rants about how it's a really awful format and it's a pain that the world uses it. But you'll come across it. People will publish models using log-p. You basically say, here's an Arrhenius expression for 1 bar, here's an expression for at 10 bar, here's an expression for at 100 bar. but they're all Arrhenius. And so in fact, these things are not Arrhenius, as we'd said earlier. And so people then say, oh, in order to try and fit it, I need to do a sum of multiple Arrheniuses. So then they say at 10 bar, add up these 3 Arrhenius expressions, and at 100 bar, add up these 3 Arrhenius expressions. And it ends up a really horrible mess and never a very good fit. And so Bill's right to hate it, but you'll come across it. People have published in it. Okay, when is pressure dependent even necessary? More often than you'd think. Quotes normal chemistry happening at 1 bar, like atmospheric conditions, lab, and moderate temperatures might be in this pressure independent limit, the high pressure limit. Challenge is most good experiments. People are good at measuring things, often at very low pressures, Futor, etc. So a lot of lab experiments are done down here at lower pressures, or maybe at higher temperatures. And so somewhere in a flame, I think, yeah, a laboratory flame experiment could be over here. As an engineer designing a engine, you might be at much higher pressures. So the challenge is it's very easy to cross over quickly from pressure independent to pressure dependent. And so fortunately, we know how to do this, but it's a pain that you have to. And often people would do experiments down here, and then you've got to be careful of interpreting the results and make sure that you know that they actually measured a PDEP rate, not a high pressure rate. And what we calculate is more normally a high pressure rate. I found in my work that when we were trying to add halogens to RMG and do flame suppressants and stuff, that we spent a long time trying to why doesn't RMG build mechanisms and tweaking rate constants and stuff, and then realized that, oh, we hadn't turned PDEP on. Let's try turning PDEP on, and everything changes a huge amount. So yeah, some of the minimal example out of the box might not have PDEP on. And so a lot of people, when they first get RMG, they start with the minimal example and tweak it to their own purposes and say, okay, let me just gradually change this to be the fuel I care about. Remember to turn on PDEP. The relationship between PDEP in RMG and PDEP in Arcane. So I think I kind of alluded to this earlier. RMG can do this PDEP automatically as it's building a full kinetic model. And it's maybe the only mechanism generator that does this. Maybe there's another, I'm not sure. Well, actually, I mentioned that in the historical note coming soon. But it, like most things, does really rough approximations. So the only way it can do this for the tens of thousands of these PDEP rate coefficients is fully automatically with very quick, crude estimates and no human input. And so that's for someone who wants a full kinetic model. So it might only get it within an order of magnitude, but it's still worth turning on because you'll be more wrong without it. RMG's general attitude is some estimate is better than no estimate. Arcane does similar calculations, often the same algorithms, and sometimes it's exactly the same classes and stuff. But it's much more suitable if you've taken one PDEP network that you care about. You calculate each well, each barrier, you find all the transition states, you do all of the accuracy calculations. But it might take you 3 months to do a network. So do that for the one after you've built your model with RMG, with PDEP on, you've done all the sensitivity analysis that Matt Johnson told us about, and you've decided, oh, this one matters, and you find that it's coming from PDEP network. Then use Arcane or Arc or something to look into the details. History.
There's one question.
Oh, yes, there's a question. Yeah.
So at high temperatures, right, there's a lot of collisions going on. So why are you saying at high temperatures, most reactions are pressure dependent?
You're at higher energy. You got more collisions, but you're looking back to my first little pictures here. You got more of this effect of things are higher and going to be falling off
Of the both one.
More, yeah, more of the Boltzmann motivations above the barrier, and so things. It takes more collisions in order to thermalize again. It's going to be my gut hand waving thing.
And you have also activating instantly.
But read this paper to be sure. Yeah, this shows that based on the size of the thing. So there's a rule of thumb, but these aren't very spread out. Even going from C3 up to C12, they're not very far apart. But yeah, this rule of thumb of when it matters. History, right? So that PDEP expansion network of kind of using an overestimate in order to gradually expand the partial network was figured out by Bill's first PhD student, David Matthew, long time ago. And he implemented it into the ExxonMobil software that Bill had been working on before he came to MIT. But Exxon wouldn't let them release it. And they were like, oh, we can't publish that. So they published the results from it. And there's a couple of papers here kind of talking about the results. But they couldn't actually share the software, which is largely what motivated Bill to make RMG open source. I was like, okay, let's start again with RMG. But then, so he said, okay, the next student started writing RMG as an open source thing, but she had a hard enough time just getting RMG to work and left out the pressure dependence. And so RMG initially didn't have PDEP. Josh Allen, around the time that I was here as a postdoc, implemented then Dave Matthews' algorithms into the RMG and added pressure dependence back to RMG. First, putting it into the Java one was a large chunk of his thesis, but the other Skunkworks project he did at the same time was writing RMG Pi. And so that's when we added PDEP to both. And first we got into the Java, and then we got it into the Python. We always had issues with kind of, it would cause issues with things like the pruning that someone added at around the same time. It's very hard to know how to prune species when they're part of a PDEP network. Can mess everything up. So it's always had difficulty, and it's a bit like, what's the analogy? I'm not sure. It's the kind of thing which people like to leave off because it sounds daunting and hard. A bit like using RMS reactors and Julia and stuff. People are like, oh, I could just leave this out of my input file. But it's rarely a good idea. So Matt Johnson then added some more options and improvements to the algorithm, and it got better. Oh, and Alon, of course, as well. So that, yeah, every 10 years, there's a major step change. I don't know when the next one, who's working on the next one, or if we're done with PDEP. But I think it's still interesting. Unsolved. I think there's unsolved stuff in there, still worth discovering. I got, oh gosh, I went faster than even Bill. Oh, there's track questions.
That was the question I had.
Oh, you got another question?
Renu, do you have a question?
Oh, yes. So this is very cool. I just you know the pressure dependency is actually the most important thing in atmospheric chemistry. So there's a lot of people working on experiments on some of the most well-recognized and important reactions like OH plus CO. So I wonder if this the mechanism from RMG or Arcane has been compared to those experiments.
Yeah.
To determine pressure dependency.
Yeah, so I would say that for small molecules that have been well studied, I would hope that we've got a good pressure-dependent description of those in a reaction library that I would put in my input file as a seed mechanism, or at least as a reaction library. RMG will then take those pressure-dependent reactions as described. They'll be parameterized like with Chebyshevs or something, and we'll just put them in the model and use them without doing this whole estimation stuff. the estimation is helpful for filling in the gaps. It can expand on networks, or if you've got new fuel molecules, it will help come up with estimates. But for the well-characterized things, I would recommend find a reaction library that has them, someone's done it carefully and put them in as a seed mechanism. Or once you've done your own, if you decided actually the initial breakdown of my fuel molecule or something is important, I do it the hard way in Arcane, put that in as a seed mechanism. I'm sure that these papers about the algorithms, about RMG, did some comparison in order to publish them. Yes, okay.
When you're constructing the master equation, is the density of states like naturally discrete, or do you assume it's like high temperature and it's continuous and then you like discretize it into little chunks?
We divide it up into grains of certain energy sizes, and rather than individual numbers of levels. But so we'll say, okay, between these 10 kilojoule per mole, like what's the density? How many different states are there in here? And then the next. So one of the parameters when you're doing this is the grain size and the number of grains, the maximum energy. So if you imagine that you've got a lot of different bins, because for every kind of column on your potential energy surface, you've then got lots of different grains. The highest you go to is one parameter. The number of grains or the size of each grain is another parameter. Properly, you should do a convergence study on those and say, does increasing the number of grains or making them smaller change my result?
If the energy is ever like super low, should you consider like looking at the actual energy states?
Oh, yeah, when they're actually discrete enough. I don't know. Not sure. I do know that some of the RMG algorithm it does some kind of tests of like, oh, in the high pressure limit, I'm not agreeing with what I expected and it will kind of say if the error is too big, it will say, try solving it again with more grains. And it will do that a few times before giving up. So if you read carefully your RMG log file, you'll often see it trying these various things of like, this looks too wrong, I'm going to try and solve it more accurately. And occasionally it will just give up. And that's often when it's then worth looking at the Arcane input file that it saved to figure out why it's struggling. Very often if it can't solve it, or it can't solve it accurately, or it crashes, or something goes weird, it's most usually a badly estimated parameter that's gone as an input. That some energy was estimated too high, or some rate is estimated too fast, or something in the input file. And so by visualizing it, you can get a good idea. I could flip through the extra slides, see if there's anything worth discussing. Yeah. Where's my Zoom? You got a question? Yes.
So if you have a well skipping reaction in the library, but then you do the pressure dependent expansion, does it recognize that you have a well skipping reaction in the library and it doesn't get confused about it?
We always get confused about it. I think it does the right thing, but what the right thing is, we keep on, it's not, philosophically, it's not quite sure what the user intends. Like, do they say, in a seed mechanism, you say, okay, I trust this to be complete. Actually, I had this problem very recently and we still haven't solved it. If RMG finds something new that you left out, that's sometimes the strength of RMG. The whole reason we use it is to discover pathways that a human forgot. And so sometimes we want it to add that pathway and say, look, you forgot this extra pathway, and it adds it. In our case, we didn't want it to do. The reason the humans left it out was because they just concluded it was too slow. And so RMG adding in its estimate was messing everything up. And so I haven't quite solved it what to do in this case. I think what it does now is it would expand the pathway, find a new route of its own, add that, but for the original ones, use the published. But then you don't know, because the original one was only valid assuming it was from a complete network. So the right thing to do is not very clear. So I wouldn't call it a bug in RMG. It's just that none of us know what's the right thing to do in this situation.
So would it be better not to put well-skipping reactions at all in the libraries?
Well, yes, but no, because then you're not using the benefit of having well-skipping reactions that someone has calculated carefully and you do trust. So if you've got well-skipping reactions that you trust, I'd put them in. But yeah, just pay attention and be careful of what it's doing. I think that maybe we'll put in a way to tell RMG, it's like, don't expand this further. Or maybe we'll put it in with a very low rate. And so it says, look, he's already told me this is slow, rather than letting RMG estimate that it's fast. But anyway, that's the type of issue you can run into. Okay, now I've got it down to 5 minutes of spare time, which is right. Extra slides. Links to documentation. Options for getting. Oh yes, we were discussing this in a hand-wavy state, but here is a few bullet points about it. 3 methods to get from your master equation to actual phenomenological rate coefficients, in pressure-dependent ones. There's modified strong collision approximation, chemically significant eigenvalues, the CSE, and the reservoir states method. Oh yes, Josh Allen did a paper where he showed that they can all be written in a similar form, and then it's easier to compare them, because everyone was using different vocabulary to describe them, and everyone was arguing about which is best. And he was like, look, they're all the same thing, just if you describe it this way. Assumptions for MSC is that a single collision will cool down your C star all the way down to thermalized C and will fully thermalize it. So you can ignore a lot of collisions to connect all the different states. You just say there's a collision that thermalized it and made it Boltzmann again. Clearly not very good, right? It's a bad assumption. But this works. So it's pretty rough, but it's very fast and it's very robust. So it's the one we recommend usually in the context of RMG, because it's not going to screw up much. And as Bill points out, that your estimates are not very accurate anyway, since they came from inverse Laplace and so on. The CSE, chemically significant eigenvalues, this you separate out the timescales between things that look like chemical reactions, because they're slow, and the energy transfer ones. And then you do an eigenvalue separation to get them. If the assumptions are valid, this is very accurate and the best approach. So if you've got really good K of E and rho of E, then use this to get an accurate K of T and P. So this is what we would often do in Arcane if you're running it. Difficulty, it's a very large matrix eigenvalue problem, can be slow, fails at low temperature, fails if your rates are all garbage, like in the context of RMG. And also has some other, when the assumptions fails, it can cause a problem. There's some ways to work around this. So it's usually the best method. The modified strong collision, the reservoir state one, has this concept that your low-lying energy levels are Boltzmann distributed. Sometimes it works, and I remember when we were like excited about using it, but then Josh showed a bunch of times when it fails, and so it just kind of works well in some cases, but we've stopped recommending it as the default. How we estimate these densities of states, I talked a little about as we came past it in the main presentation, the inverse Laplace transform. We first of all estimate as many vibrational frequencies as we can from a library buried in the database of StatMech stuff. And so I noticed a student of mine when he was adding halogens to RMG, like chlorine, bromine, fluorine, etc. We suddenly realized, oh man, in order to turn on PDAP, I think this might have been why he didn't originally, we needed to add to that database as well all the functional groups. So, okay, what if you've got a methyl group with 3 chlorines on it? What's the vibrational modes for that, etc. So if you're the kind of person who's extending the chemistry of RMG, don't forget that file. because without those vibrational frequency estimates, all of this speed-up stuff doesn't work so well. And then the ones that it can't estimate, it figures out from inverse Laplace transform. Oh yeah, and also because the inverse Laplace transform is used to get K of E from K of T, if your K of T isn't actually for the high pressure limit and has a wacko T to the N term in and is something weird, then we'll really struggle to do the ILT. And so there's challenges there. Blah, 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 blah. Oh yes, difficulties with pruning. Finer mesh, right? Yes, this is about the number of energy grains that you were asking about. Yeah, you should really vary them to converge.